We're going to continue this discussion of partial fraction decomposition, but we're going to look at what happens when you have quadratic factors mixed in with your linear factors. So with this one, I do see that the degree of the numerator is less than the denominator. Go there. I'm going to factor the denominator, and all I can really do here is factor out an x, which leaves me with x times x squared plus 1. We see that this is linear and this is quadratic. So the decomposition, x squared minus 1 over x times x squared plus 1, is going to be a over x because this one is linear. Because the second one is quadratic, we need to put whatever the next letter in the alphabet is, which is a b, times x plus c. So remember, the goal is usually to have a natural log u prime over u integral. And in order to do that, if your u is x squared plus 1, you're going to need an x in your numerator to make that happen. So that's why we have to use this decomposition format. So I'm going to go through and use a very similar process to what I was doing before. I'm going to multiply by x times x squared plus 1 because that's the denominator that I want to cancel. I will cancel what cancels. Everything here, x here, x squared plus 1 here. I'm going to write it out as x squared minus 1 equals a times x squared plus 1 plus bx plus c times x. Now at this point, you can try to pick some value that would make everything cancel. I think the A is not going to really help you with B and C. So I am going to show you the other method, and this does work with every partial fraction problem. So if you like this better, you can do it the same way every time. Less of the kind of having to figure out a trick. Basically what you want to do is leave the left-hand side the same for now. We're going to distribute and FOIL and whatever we need to do to the right-hand side to get everything multiplied out. So I'll have ax squared plus a, and I'll have bx squared plus cx. On the right-hand side, I'm going to collect my like terms. So I notice that I have two x squared terms. So I'm going to group them together, and I'm going to factor out the x squared, which will leave me with a plus b times x squared. I have one x term, and I have one constant term. So now what I'm going to do is I'm going to look at the left-hand side. It is x squared minus 1, but I notice that I'm missing an x term. So really what we have going on here is x squared plus 0x minus 1. Now the reason why this is interesting is because I want to go from left to right. I want to pair up the matching coefficients. So for x squared, I have a plus b on this side, and I have an understood 1 on this side. So because these two polynomials are equal, they have to have the same coefficient. So that means that a plus b has to equal 1. For the x term, I have a c and a 0, so that means c has to be 0. And for the constant term, I have an a and a negative 1, so that means a has to equal negative 1. So what I've created is a system of linear equations that I can solve. We already know that c equals 0 and a equals negative 1. So we just need to find b, and we can plug in a equals negative 1 into the first equation to get that b equals 2. So my decomposition then, going back to the original format, we're going to have, let's see, a is negative 1, so we'll have negative 1 over x plus bx plus c plus 0 over x squared plus 1. And that's what we want to integrate. So the integral of x squared minus 1 over x times x squared plus 1 dx is equal to the integral of negative 1 over x dx plus the integral of 2x over x squared plus 1 dx. I can bring the negative out front. I might want to bring the 2 out front, but I'm going to actually leave it there because if u equals x squared plus 1, u prime would be 2x. So we have the u prime over u that we need. So this one is negative natural log of the absolute value of x. And then this one is the natural log of the absolute value of x squared plus 1, all plus c. And you can leave it like this, or if you prefer, you can collapse the logarithm and have the natural log of the absolute value of x squared plus 1 over x plus c. Either way is fine. It's possible that you may also have some repeated quadratic factors. So for this one, notice that it's already factored, but your denominator is x squared plus 2 squared. X squared plus 2 is a prime polynomial and it can't be factored any further. So this is a repeated prime quadratic factor. So I'm going to try and find the decomposition for this one as well. So I've got 8x cubed plus 13x over x squared plus 2 squared. And because my first factor is squared plus 2, which is quadratic, I'll have b. Because it's repeated, I need another copy of it, just going up to whatever power it is. In this case, it's 2. And since it is quadratic, I'm going to write this one right along the alphabet until I run out of letters. So we're going to go through the same process we always do. We're going to multiply through, and we'll multiply through by the denominator, which is x squared plus 2 squared. We'll cancel where we can. And we'll rewrite our equation with no denominator. We'll have 8x cubed plus 13x equals ax squared plus 2 plus cx plus d. And again, there's nothing I can really plug in to cancel everything out, so I'm just going to use the straightforward method that works every time. I'm going to FOIL all this out, and then I'm going to equate the corresponding coefficients. So leaving the left-hand side the same for now, foiling here, I get ax cubed plus 2ax plus bx squared plus 2b, and then this is just cx plus d. So now I'm going to collect the like terms. So I notice I just have the 1ax cubed. I've got the 1bx squared. I've got 2ax and cx, so we'll factor the x out of that to be 2a plus c x. And then as far as constants go, and I mean constants with respect to x, we have 2b plus d. On the left-hand side, I notice that I'm missing the x squared term and the constant term, so I'm just going to fill in zeros for that. So now we're going to set our corresponding coefficients equal. So the first one I'll have is a and 8, a equals 8. The second one I'll have is b equals 0. The third one I'll have is 2a plus c equals 13. And then the final one, the constants, will be 2b plus d equals 0. So this is really easy to solve. Thankfully, we already know what 2 of the variables are. So to find c, we'll have 2 times 8 plus c equals 13. So that's a 16. So we get -3. And 2b plus d is 0, so 2 times 0 plus d equals 0. So I actually get d equals 0. So my decomposition, going back up to the original setup, ax plus b is going to be 8x plus 0 over x squared plus 2. And then we're going to have plus cx plus d will be -3x plus 0 over x squared plus 2 squared. Okay, so I'm going to integrate that. So the original integral I wanted was the 8x cubed plus 13x over x squared plus 2 squared. So I'm now going to be integrating 8x over x squared plus 2 dx plus negative 3x over x squared plus 2 squared dx. So now what I'm going to do is I'm going to bring out constants and get this into a better form. So I have 8 times the integral of x over x squared plus 2 dx. Here we'll have minus 3 times the integral of x. Let's make this x squared plus 2 to the negative 2 dx. Now in both of these integrals, our u will be x squared plus 2. So du will be 2x dx. In both cases, I have the x I need, I just don't have the 2. I'm going to have to multiply on the outside by 1/2 to account for that. So this integral is 4 times the integral of u prime over u dx. And this one is negative 3/2 times the integral of u to the negative 2 du, because this would be my du. So I get 4 times the natural log of the absolute value of u. Let's just go ahead and plug that in, which is x squared plus 2 minus 3/2 times u to the negative 1 over negative 1, so negative 1 over u. And of course we can replace u with our x squared plus 2. And then we need a plus c. And finally, just to clean it up a tiny bit, we would have 4 times the natural log of x squared plus 2. Since this is positive, I don't need the absolute values there. X squared plus 2 will never be negative. Plus 3 over 2 times x squared plus 2, all plus c. And I would leave it there. I would not go any further. Keep in mind as you're working these problems, most of the time you are going to end up with some kind of natural log or some kind of u to a power, but that's not always the case. There may be some problems where you have to do trig substitution in the end. There may be some problems where you end up with like an arcsine or an arcsecant or an arctangent. Any valid integration that we've done up to this point could appear at the end of one of these problems. Just want to make sure that you are aware of that. Let's look at this example. Notice that we've got an x cubed in the numerator and an x squared in the denominator. So we do not have a numerator that is less than the degree of the denominator. So what I would want to do with one like this is I would want to start out by using long division. So I'll put x cubed, let's fill in placeholder 0x squared minus x plus 3. I'm going to divide by x squared plus x minus 2. X cubed divided by x squared is an x. When I multiply through, I get x cubed plus x squared minus 2x. I change the signs of all three of these and cancel where I can. So I get negative x squared plus x plus 3. Negative x squared divided by x squared is minus 1. So I multiply back through, negative x squared minus x plus 2, and change the sign to subtract. And then I get 2x plus 1. So what this means then is that I'm really integrating x minus 1 plus 2x minus 1 over the denominator x squared plus x minus 2 dx. Now these two pieces are going to integrate just like you expect them to. The integral of x dx minus the integral of 1 dx, and then plus the integral of 2x plus 1 over x squared plus x minus 2. And from there, you may notice that we actually don't need partial fraction decomposition, because in this case, u would be x squared plus x minus 2, u prime would be 2x plus 1, and we have u prime over u, which is everything we need. So if you recognize that, great, you don't need it. If you don't recognize it and you don't go straight to the natural log of the absolute value of x squared plus, you absolutely can work this by partial fraction decomposition. It'll take you a little longer, but if you do it correctly, it will get you to the right answer in the end. So you can do it that way, but sometimes you don't need it. So be careful with this. You know, always check for u prime over u before you jump into partial fraction decomposition, because it may not be necessary. There are also some special cases where you may not realize that you have a partial fraction decomposition, like something like this, the integral of sine of x over cosine of x plus cosine squared of x dx. So if I were to, for example, let u be cosine of x, du would be the derivative of that, which is negative sine of x dx. And if I multiply by a negative on the inside and the outside, I now have the du that I need. So this is negative integral of 1 over u plus u squared du. And this is something that we can integrate using the partial fractions method, because u plus u squared is equal to u times u plus 1. So the partial fraction decomposition, 1 over u times u plus 1, or u times 1 plus u if you keep it in the format, either way, would be a over u plus b over u plus 1, because both of those are linear. I would multiply through by the u times u plus 1, just like I've done before, to cancel what cancels. I get 1 equals a times u plus 1 plus bu. At this point, I can either multiply out or I can choose values of u. I think I'm just going to multiply this out. I get au plus a plus bu. And if I factor out a u from the terms that have it, I'd have a plus b times u plus a. There's an understood 0 u over here. So that gives me a plus b equals 0 and a equals 1. So using substitution, I would get b equals negative 1. So my integral now, this is kind of my scratch work out here, would be the negative of the integral of 1 over u minus 1 over u plus 1 du, which is negative integral of 1 over u du plus the integral of 1 over u plus 1 du. And both of these are natural logs, because this would be negative natural log of the absolute value of u plus the natural log of the absolute value of u plus 1, all plus c, or the natural log of the absolute value of u plus 1 over u plus c. And then, of course, don't forget to plug back in your u. This would be the natural log of cosine of x plus 1 all over cosine of x, all plus c. So there may be some problems that you have to use u substitution and then end up getting something you can deal with partial fractions. And the way you would recognize something like that is this is a polynomial in terms of cosine of x. So if you have a situation like that, this may be the best approach for you to take.